Alright, so today we'll be doing different operations with matrices. So with my students, I always start with our prior knowledge, seeing as everything always ties back to these different properties. So we'd review our identity property, our inverse property, our associative property, and also our commutative property. And so just recalling that the identity is 0, anything plus 0 is itself. The identity for multiplication is 1, anything times 1 is also itself. And then for the inverse, we're always trying to equal our identity. So for addition, we're adding the opposite. Multiplication, we're going to multiply by the inverse or the reciprocal. And we're always going to equal the identity. So addition, when we add them, will equal 0. And for multiplication, when we multiply them, we'll get 1. We won't really use the associative property today, but it's just saying we could change our grouping and it won't change the answer. And for the commutative property, we are going to talk about this today, so we'd review this where we could change our order and we're still going to get the same answer, and this holds for addition and a multiplication. And so for our matrices, we do have an identity property and an inverse property, and then we're going to do a few different examples and see about our commutative property. So identity for addition, our identity is the 0 matrices, where it's 0, 0, 0, 0. Anything plus this matrix will always give you itself. Our multiplicative identity is the 1, 0, 0, 1. If we multiply by this, we're going to get itself as well. For the inverse, it's also going to be equaling the identity. And for addition, we're going to stay adding the opposite. So if I have a matrices here, 2, 1, 4, 7, by adding the opposite, we're going to equal the identity and get this 0, 0, 0, 0. For multiplication, we're also going to stay multiplying by the inverse or the reciprocal. So this is actually the inverse. So here is our matrix, and this was actually B in our example, and then this is the inverse of B. And when we multiply these, we're going to get the identity matrices, which is the 1, 0, 0, 1. Now, to find the identity, how did we get this negative 1, negative 3, 1, 2, and I'm sorry, not the identity, to get this inverse, what you're going to do here is actually use a determinant, and so the determinant is AD minus BC. So for here, I had to do 2 times negative 1 and 3 times negative 1, and when I did that, the determinant was actually 1. So I just changed the order a bit here, and instead of A, B, C, D, we reversed it and got D and A here, and then did the opposite of C and the opposite of B. And that's how we got that matrices here, and when multiplying them, I get my inverse. And we could actually reverse this and multiply the inverse and the matrices and also get the identity. So now what we're going to do is try two separate problems. So we're going to do adding, and then after we finish that, we'll try multiplication. So when we're adding matrices here, I have this matrices 2, 1, 4, 7, and that's A. And then B is 2, 3, and negative 1, negative 1. So first we're going to add A and B. So I'm going to add 2, 1, 4, 7, and 2, 3, negative 1, negative 1. So when we're adding matrices, we're taking things in the similar places and we're going to add them. So here I have my element 1, 1, and this is my element 1, 1 because I'm in row 1, column 1. Or I reverse that, sorry. Row 1, column 1, row 1, column 1, and so we're going to add those numbers. And so we'll have 2 plus 2, and we actually did that here, so I have 2 plus 2. Down here I'll have 1 plus 3. I'll have 4 plus negative 1 and also 7 plus negative 1. And so we're doing addition just like we would before. And so 2 plus 2 is 4, 1 plus 3 is 4, 4 plus negative 1 is 3, and 7 plus negative 1 is 6. So when we add these two matrices here, we actually get the matrices 4, 4, 3, 6. So we're going to try doing the opposite and do 5 plus, or I'm sorry, B plus A. And so we're going to reverse that and see if this is commutative. So if it was commutative, we know that A plus B and B plus A will be equal. So we're hoping that underneath this green box is another 4, 4, 3, 6. So we rewrote and we have B and A, and we're going to add our like elements together. So we're going to have 2 plus 2, 3 plus 1, negative 1 plus 4, and negative 1 plus 7. And if we look here, everything is actually, we are reversing them as we're changing the order. And so when we do it, 2 plus 2 is still 4, 3 plus 1 is still 4, negative 1 plus 4 is still 3, and negative 1 plus 7 is still 6. So because these are the two same matrices, we do know that this does hold. And so the commutative property does hold for matrices. Now for multiplication. So now we're going to multiply two matrices, and this is going to be a little different and not as simple. So what we're going to do here is do A times B. So we have our same matrices for A and B. And so we're going to do A times B, then we'll try, oh, this is actually a typo, hoping that this is not the same one underneath of it. It's not. So this is actually B times A, so let's fix that quickly. Sorry. And so that's actually B times A. So here we're going to do A times B, and the way that we do this is we take row 1 and multiply it by column 1, and that will give us our first element. So we're going to multiply 2 and 2 and 4 and 3, and we're going to add that together to get our first element. And then we're going to multiply row 2 by column 1, and that'll give us our second element. Then we'll multiply row 1 by element or column 2, give us this element here, and then row 2, column 2 to give us this element. So I'm going to have 2 times 2 and 4 times 3, so that's 4 and 12. Then 1 times 2 and 7 times 3, it's 2 and 21. 2 times negative 1 and 4 times negative 1 gives us negative 2 and negative 4. And then we have negative, or 1 times negative 1 and 7 times negative 1, so that'll give us that. And then we're just going to finish this up. So 4 plus 12 is 16, 2 plus 21 is 23. Oops. Negative 2 and negative 4 gives me negative 6, and then I have negative 1 and negative 7 gives me negative 8. So A times B will give us this element. So now what we want to see is this answer here for our matrix the same as going to be what's under this green box, is that's B times A. So what we're going to do is flip our order, see if this commutative property holds. So we're going to have B times A, and we're going to do the same thing here. So we're going to take row 1 times column 1, and I put that here for the first element. Then we're going to do row 2, column 1 here. Then we'll have row 1, column 2, and row 2, column 2, and that'll give us our different elements. And so when we solve our math, we actually get down to here. So I have 4 and negative 1, 6 plus negative 1, 8 plus negative 7, and 12 plus negative 7. And so if we finish that math, we're actually going to end up with a matrix negative 3, 5, and 1, comma 5. And so if we look, the commutative property does not hold. And this actually confused me for a little bit. I thought I messed up my math and actually redid both of them multiple times to check and see. But the commutative property does not always hold for matrices. All right, thank you.